I apologize for the lack of videos recently. I've been sick this past week and unable to make them, but I'm alive now and ready to continue the series. So, what is a derivative? It's essentially a function that tells you the instantaneous rate of change at any point of a given function. So, if you had this distance time plot, its derivative would be a velocity time plot, since velocity is the rate of change of distance. So exactly how would we compute such a velocity time graph? The first thing to start off with is slope. Slope is the rate of change, as in, if an oil company is selling 50 barrels per day, that 50 would show up as how many barrels it gained over a single day. So to calculate slope, we want to know the change in the y direction compared to the change in the x direction. Again, using the oil selling comparison, if the company had sold 25 barrels on day 1 and then sold 75 barrels on day 6, then when we attempt to find the slope, we'll subtract 25 from 75 to find the change in barrels, and subtract 1 from 6 to find the change in time. Now, to find the slope, we divide the top change by the bottom change to get 50 barrels over 5 days, or 10 barrels per day. With slope under our belt, let's express this as a formula so we can quickly refer to it. When we write it using the Greek letter delta to represent change of, slope equals delta y over delta x, the change in the y coordinate divided by the change in the x coordinate. Or we could write it as y2 minus y1 divided by x2 minus x1. When we have a specific function, y2 is really f of x2, and y1 is really f of x1. So now we can write out the slope formula using our function notation. Slope equals f of x2 minus f of x1, all divided by x2 minus x1. So that worked out nicely for our straight lines. But what about a curve? When I take this parabola, f of x equals x squared, when I take these 2 points and draw what is known as a secant line, which is just a line between any 2 points on a function, it doesn't perfectly match the curve, and is really just an approximation. However, when I draw this line that is just touching the curve, I can represent the rate of change at just that point. I can draw what is known as a tangent line. So to get that tangent line, all I have to do is make secant lines that closer and closer and closer to touching just the curve only once. Using our slope formula, let's say we are trying to find the slope of this parabola at x equals 2. So we'll draw a secant line up to where x equals 3. Plugging this into the formula, we get a slope of 5, which isn't too bad, as you'll see in a moment. Now, 3 can be expressed as 2 plus 1. So let's express our distance to 2, half that, and try 2 plus 0.5, or 2.5. When we plug this into our formula, we get a slope of 4.5. Now, we can keep getting closer and closer and closer like this, or we could use the limit, which is designed to get infinitely close to something, and then we'll have the instantaneous rate of change. As we did before, let's look at adding a number, let's say h, to 2 to get the x value where we're approximating with. We write down our slope formula. It is f of 2 plus h minus f of 2 all divided by 2 plus h minus 2, which simplifies to f of 2 plus h minus f of 2 all divided by h. Now all we have to do is write down the limit as h approaches 0, and then we'll find our instantaneous rate of change. So let's go ahead and solve this limit. We'll plug in our function up top, and then we'll notice that if we plug in h equals 0, we would have to divide by 0. So we'll have to do a few things first before we just plug 0 into h. Let's start by expanding that 2 plus h term into 4 plus h squared, and the 2 squared into 4. After we cancel out the 4's, we're left with the limit as h approaches 0 of 4h plus h squared all divided by h, which, when we cancel out the h's up top with the 1's on the denominator, we are left with the limit as h approaches 0 of 4 plus h, where we can now substitute in 0 for h because we're no longer dividing by 0. and get that the instantaneous rate of change for our parabola at x equals 2 is 4. Now, finding it at one point is nice, but what about finding it at all points? Here comes the derivative. Instead of saying x equals 2, why not just plug x into the formula? If we did, we'd do all the same algebra, but instead it would cancel out to 2x as opposed to just 4. To name this derivative, two common notations are Lagrange's notation, which is to call the derivative of a function f prime of x, where the prime represents that you took the derivative of the function, and Leibniz notation, where we write a lowercase d instead of the deltas in our slope formula to show instantaneous rate of change. Other words for the derivative are differentiation, which is the process of actually taking the derivative, and instantaneous rate of change. That's enough just to get a feel for what the derivative is. In next video, we'll go through examples of derivatives of every simple function. And after that, we'll get into covering some of the ways to make differentiation even easier. Until next time, keep on learning.